I'm actually very pleased to welcome our first guest speaker from the academic world. And the next presentation is titled Stealthy Fingerprinting Users with Personalized Blocking Rules. And our speaker is called Elhaj Sheda Hard. And he's a PhD candidate at the EPFL, Swiss Federal Technology Institute of Lausanne. And Said's research focuses on security and privacy leakage from browsers and web ecosystems. And his presentation basically reveals that customizing app blockers with specialized filter lists can inadvertently actually make users more vulnerable to fingerprinting and tracking. And he's also detailing 4 novel attacks to expose which filter lists are active. But no worries, Said's talk has also recommendations for protections against specifically this type of fingerprinting. So that said, welcome to the stage, Said.
Thank you, everyone. So let me just figure out this clicker thing. Okay. So yeah. So I will be presenting to you my recently published work in Usenix, which basically tries to uncover attacks to fingerprint ad blocker configurations. Okay. So a bit about myself. I'm a third-year PhD student in EPFL, Switzerland. I do web privacy research. I've worked on web extensions, browser internals, and currently looking into server-side web measurements. So users on the web browse the web with varying levels of privacy protections. The majority of layman users browse the web with no protections at all, and then they're susceptible to more traditional forms of tracking, like cookie-based tracking, and a bit more private users use popular tools like ad blockers to try to block these cookie-based tracking and more traditional techniques, but are still susceptible to more advanced forms of tracking, such as browser fingerprinting. And here comes at the tail of the distribution our kind of privacy power users, the prime customers of privacy, who use all sorts of available tools and heavily customize their setups to block all these more advanced forms of tracking. And there is the underlying assumption that the more tools you use or the more advanced setup you have, the more private you are. And in this work, we question this very assumption. So it is true that by using more tools, you block more different types of tracking, like cookies, IP fingerprinting, and even browser and device fingerprinting. However, users have this kind of implicit assumption between the layers of tools they use and their increased privacy, and we refer to this behavior as pet layering. However, in our work, we show that we can immediately reduce their anonymity online by simply exploiting one layer of their defenses, which is fingerprinting their ad blocker configurations. Now, browser extension fingerprinting is a mature field where attackers try to uncover the list of extensions a user has installed. And some of this work already tried to discuss this question. So does including privacy extensions make you more fingerprintable? But they brushed off this worry immediately, saying that their contribution to the fingerprint is minimal. Without them, the fingerprint quality is still good, so might as well add them for their blocking benefits. However, in this talk, we will show that we can extract more bits from the extension, and then their contribution to the fingerprint is actually very, very large, and it could cause major harm. Sorry. Yeah. So just a bit before, I think most of you are aware that ad blockers come with varying levels of settings, or what we refer to as filter lists, and most of them come with the default filter lists activated, which blocks traditional forms of advertisements and advertisement boxes. However, you can also add different other filter lists to block special elements, such as social media buttons, cookie notices, or block fingerprinting domains. So in this work, we will primarily answer how can we quantify this privacy threat on these privacy-conscious users or our privacy power users. And in this talk, we will answer 3 main questions. How is this different than prior fingerprinting attacks? Can a malicious website fingerprint the configurations reliably? And how good is this fingerprint in reducing user anonymity? Starting with the first question. So in prior work, as mentioned earlier, attacks try to detect whether you have an extension or not, revealing one bit of information. However, in our work, users having an ad blocker will have different fingerprints, which is related to the configuration of their ad blocker. So we reveal more bits per extension, and we distinguish between users having an ad blocker. The second degree of difference is by our target users. So as described earlier, users on the web can be distributed based on the tools they use. So some of them might use a privacy-focused browser, others could use a privacy extension, some could use both because they think it makes them more private, and finally some could use Tor, for example, for network protections. And at the middle there, we see our privacy-conscious users who would like to use all tools to be more private. Okay, so traditional attacks try to maximize the users they can uniquely identify from the global population. And they mostly succeed at the fringes, where users use one or maybe no defenses. However, users in the middle who are privacy conscious will thwart these attacks and will be indistinguishable from each other based for this attack. And they will have the same anonymity set size. And the anonymity set is basically the set of users having the same fingerprint. In our attack, we primarily just focus on these privacy-conscious users and try to segment these anonymity set while ignoring the users on the fringes because, as we said earlier, they're already susceptible to other types of attacks. Now, moving on to the second question, how can a malicious website fingerprint this configuration? So as we mentioned earlier, for each filter list, we have multiple filter rules which dictate whether to block a certain network request or hide a certain element, labeled as blocking rules or cosmetic rules. So two users having two different filter list configurations will have two different sets of active rules and end up with two different states for the same web page. Now, our job as an attacker is to extract back which rules were active and try to reconstruct which filter list configurations they have. However, since we are targeting privacy-conscious users, they will likely have installed state-of-the-art fingerprinting detectors, which try to look for signatures in JavaScript files for fingerprinting behavior and try to block those. So our attack must not use any JavaScript, and we try to rely strictly on stylistic or scriptless fingerprinting, which is a newer technique. We also want to use as few possible offer requests as possible to not raise any alarms for the user. So we must constrain the number of tests we conduct on the browser. We discover three different types of attacks on three different browser features to show that the attack is kind of inherent to the activity of blocking something and not just a simple bug in the browser. So I'll be discussing two of these attacks at length, starting with the first, which is the CSS animation attack. So the CSS animation attack relies on two key facts. First fact is that when ad blockers try to block a certain element, it hides it using a CSS rule. And the second fact is that browsers, as an optimization, do not execute any CSS code for hidden elements. So to detect a certain rule, if a rule is active and we set the background image to resolve to an attacker domain, the image will be hidden because it's blocked, and the network request for the background image will never reach the attacker. However, if the rule isn't active, the background image will get resolved and the request will be sent to the attacker as a signal. Now, we must add a 1-second delay because some of the ad blockers do not immediately block the image, and it will take some time, so we need to take account for that. Moving to the second attack. So for the image lazy loading attack, so lazy loading is a feature added by browsers to make sure that images that are beyond a certain boundary from the user viewport are not loaded, so that it's optimized. And we can simply just stack an element that should be blocked on top of an image in a way that it doesn't cross the boundary. Now, if the rule is inactive, the element will stay and the image will be below the boundary. However, when the element is blocked, the image will cross the boundary and sending sending a signal to the attacker. So now that we know how we can fingerprint a specific rule, we still have to decide which rules we want to fingerprint, because there are more than 100,000 rules. And we want to find the smallest possible sets of rules to fingerprint. We rely on two key facts, is that users configure ad blockers based on a filter list granularity, not a rule granularity. So it should be enough for us to find a unique rule per list to fingerprint the list. However, filter lists could have shared rules, and some filter lists don't have to be unique necessarily. And for those, we can make associations between rules we can detect and the possible filters that should be active if they are active, if these rules are active. And we call these associations equivalence sets. Just a term that we use. Okay. However, the number of equivalence sets is still large, so we need to choose from these equivalence sets the minimum possible so that we can provide the most unique user fingerprint. So it's a compromise between the size of the fingerprinting vector and the user uniqueness. And for that, we rely on a prior work by Gulles et al., which provides two different algorithms in two different settings to find the best possible fingerprint tests to perform to maximize the uniqueness of the user. The first setting is targeted fingerprinting, where we want to target a specific user, and we want to find, for example, the best 10 tests to perform to find whether this user is the one browsing or not. And the second setting is general fingerprinting, which takes in a set of users, and we want to maximize minimize the average anonymity set size for these users using only, for example, 10 tests. Finally, we want to see how good is this fingerprint in reducing user anonymity. So we perform an evaluation over public data sets extracted from ad blockers. So normally, users, when they submit reports to the ad blockers for issues, these issues will be submitted automatically to GitHub for some ad blockers. And these issues will often include which filter lists were active at that point of time. So we compile a data set from these GitHub repositories. And we mostly rely on two of the popular ad blockers that provide these lists publicly, which are AdGuard and uBlock Origin. They also have a very large number of filter lists, so the fingerprint should be diverse enough. And we collect around 18.5 thousand users for AdGuard and 5.9 thousand users for uBlock Origin. Here we see that looking just at the configuration entropy, we see that the entropy is within the bounds of the literature, which means it should be a good starting point for studying our attack. Now, if we want to evaluate our attack, we must first know that for the stealthiness of our attack, different filter rules are not equal. So cosmetic rules are considered more stealthy because they will only send a network request to the attacker if the rule is active. Because when it's blocked, we will send a signal to the attacker, for example. However, if it's unblocked, there's no necessary network request. Unlike cosmetic rules, blocking rules will always send a network request either ways, either to the blocked domain because the rule is inactive, or to the attacker domain if the rule is active. So now we want to see how much of the filter list we can cover by detecting different types of rules. So starting by cosmetic rules alone, which is like the most stealthy approach, with just 15.3% of their generic cosmetic rules. It's not moving. Okay. We can detect around 27% of equivalences and get up to 73% of the filter lists. Now, if we augment this to using all our generic rules, including network rules, we can cover 55% of rules and increase our filter list detection to 89%. Moving on to user anonymity. So The reputable literature mostly caps out at 30% for uniqueness. So that's basically what we take as our benchmark. And we find that if we rely only on generic cosmetic rules, we can, with only 29 rules, we can uniquely re-identify 16.92% of our users. And this, without any constraint, this increases to 22.25 users. Now, if we increase the rules that we can detect, we can, with 30 rules, we can detect around 19.3%. And without any constraints, we can get around 24.9%. And finally, we describe a theoretical attack with an iframe at the center so that we can try to detect not only generic rules, but rules that apply for specific domains. And we find that at most, which is the cap, basically, we can get around 26% for the unconstrained case. We also measure the Shannon entropy of these different attacks. And we find that even with just using the generic cosmetic rules, we can match the dataset entropy, so the configuration entropy. We can almost match the configuration entropy, which means that even if we don't get a lot of unique users, we still reduce the anonymity set sizes overall, and we have very diverse fingerprints for users. And we also overshoot the fingerprint entropy for prior work. Lastly, and the most important figure probably, is the following, where we plot and we distribute users based on the number of changes they do to the default configuration compared to their anonymity set size on the y-axis. And we can clearly verify our hypothesis as we show two different community of users. We have the users on your top right. Yes, on your top right, which is the community of users that don't change their configurations by much and have very high anonymity set size, which means they are not very uniquely identifiable. And then on the below, we have the users that perform a lot of modifications and then in turn have very small anonymity set size, often identifiable among 8 users. We also perform a fingerprinting stability study where we look for the rules that we use in our fingerprints and see how old they can go, and this would give us a measure of how far in the future they can stay. And we see that if we use our equivalence sets, which have a redundancy in rules, we can have up to 3 years of stability in equivalence sets. Now we also discuss how detectable these attacks are. So we measure the network overhead, and we find that it is within bound of the benign website. So if you want to just make a network-based detector, based on volume at least, it will have a lot of false positives. We also are immune against state-of-the-art detectors because we don't use any JavaScript. Now for mitigations, we discuss 3 different mitigation strategies. The first one is a very naive one where you just say, okay, don't allow customization, what could happen? And then the biggest bottleneck would be performance, of course. And then, so we measure how much of this performance decrease. And of course, the second issue is breakage. So breakage increases because now you will allow niche filter lists to the global population of users. The second approach is to just globally allow the rules that will contribute to the fingerprint. So we basically play a small game where iterative game, where we first find which rules are used for the fingerprint. We enable them globally, basically removing them from the candidate list of rules. And then we measure, we try to find new rules that will contribute to the filter list. And we do this again and again, which eventually will decrease the entropy because more rules are now globally applied. And we find that the result really depends on the threshold of entropy that you will tolerate as a developer. So if you want to get to 0.2 normalized entropy, you have to enable a lot of rules, which will again hurt performance and might cause breakage. And lastly, we do a web measurement study to see if the browser features that are used in our attacks are very used or not used at all, so that we can maybe remove them or ask browsers to remove them or block them entirely. And we find that if we just want to do it at the feature level, many websites still use these features, so we cannot just block them entirely. So we have to do a bit more granular decisions on blocking, which, again, could cause breakage. So my takeaway is that this attack is not marginal. Our privacy users, which are basically our prime customers, are at some point of a risk, and there is an inherent cost to personalizing privacy extensions that we have to just take in. And even if the fingerprinting does not uniquely re-identify people, some profiling could still happen. For example, if you detect certain language lists or certain lists that are bound to certain subset of websites. Now, for different stakeholders in the community, for ad blockers, I would invite them to use our pipeline to try to maybe remove problematic rules, since they have also access to much larger data sets of users, and try to reduce reliance on generic rules, which in a sense are the easiest to try to detect, and also maybe find other ways to hide elements without triggering CSS leaks, such as optimizations that will not execute certain JavaScript or CSS. For the privacy power users, it's just a matter of increasing the awareness and trying to communicate better that privacy is a complex metric. It does not increase linearly with using more tools. And lastly, for browser vendors, is to evaluate the CSS leaks that come from different optimizations before adopting these features. So, for example, our third attack is just an experimental attack on an experimental feature, which is the CSS container style queries, which basically queries styles from one component to the other and can trigger conditional CSS. So this could leak CSS. Also, I found kind of new features that amplify this risk even further beyond like the results that we found. And the first of them is automatically activating certain lists based on what the user browses. This includes language lists, for example, which was, I think, at some point enabled automatically in AdGuard. And the second and most worrying is kind of this new trend of element zapping, where users are invited to select elements from the page that they would like to remove, which is essentially allowing users to build their own filter list that is most probably uniquely bound to them. Okay. Yeah, and with that, I think I'm done. So I just try to describe to you that users with advanced privacy setup are kind of uniquely susceptible to these fingerprinting risks, which is counterfactual in a sense. And then we provide practical scriptless attacks with high entropy, which is similar to prior work. We also validate the stability of our fingerprints, try to provide mitigation strategies and recommendations for stakeholders. Thank you very much.
Hi there. A really cool talk and a lot of things that a lot of people don't think about. Two questions. One, well, now I'm blanking. One, what are your go-to recommendations for maybe a regular person who does want more of those advanced techniques but wants less of these concerns? Like I know Brave has some of their own anti-fingerprinting measures, and now we have Adblock Browser that at least tries to target this. So did you do research on what's the most effective tools for those people to be using?
Yeah, so I mean, that's basically what my whole paper is trying to do, is to just increase awareness and understand that there are inherent kind of compromises, right? And they're inescapable compromises. And this is just one example of them, that essentially if you have any tool and that you want to personalize, this personalization will kind of kick back at you, right? So kind of to be far from the crowd. In the end, if somebody can detect how far you are from the crowd, this will itself come back and become an identifier for you. So, yeah.
Got it. And then my final question is, how are you, and I guess this is a question for myself and maybe a broader one, but are those trade-offs worth it? Because are we able to measure the likelihood of maybe those extra things that people are doing helping their privacy, and maybe the percentage of people using these advanced fingerprinting techniques is very small? So are we able to maybe measure how much this impacts?
Yeah, so very, very good question. And the main challenge against studying such things is that we're really targeting in our study privacy-conscious users. And most often these users will be reluctant to participate in studies that reveal anything about them, right? So to study this effectively, we would have to ask them which websites they visit to see the impact of the extra blocking impact on their experience, right? So it's kind of a very hard question to maneuver. I think we need not only privacy-preserving measurement techniques, but something that's psychologically acceptable to them to be able to measure this.
Oh, thank you.
Thank you so much for the talk. It was super interesting. Couple of questions. So you mentioned that this is a scriptless technique. And as far as I understand, correct me if I'm wrong, the point is that the signal via CSS will be, in the end, it will be a web request.
Yes.
To some fingerprinting server.
Yes.
So basically, does that mean... isn't it true that we can observe these signals and prevent these requests? So basically, we're back to square one when we have to add all this stuff to the filter list.
Yeah, so you go back basically to the cat and mouse game, right? Of people using this and then changing their domains and kind of doing domain rotation. But definitely, one of the detection techniques we discuss is using more advanced detectors that use graph representation of the page interactions, right, to find the patterns in the network requests. So that's one of the detection techniques.
One more question. So as far as I know, fingerprinting is mostly used by ad tech companies that would like to, track people without using cookies. And there are just a limited set of solutions that they use it. For instance, Fingerprint.js, which is the most popular one.
Yeah.
Does it use any techniques like that to fingerprint the user?
Yeah, so Fingerprint.js actually, I think somewhere around where I published the work, released a blog post about exactly trying to fingerprint ad blockers as well. So I think it's worthwhile to look at that. I think they use similar techniques, but maybe less advanced techniques.
So they don't try to do scriptless, right?
Not as far as I recall, but scriptless attack have been described, I think, by more than 3-4 academic works. So they've been in a while in the community. So if some bad actor would have picked it up, it's very possible that they would do.
Got it. Thank you so much.
Great talk.
Thank you.
You mentioned a potential mitigation from the side of browser vendors. I'm curious if you have any thoughts on if that is sufficient or if there are actually going to be more leakage cases that would be used after that is fixed.
Yeah, so I don't provide an exhaustive list of all features that would cause leakage. I think that by just having a mindset of keeping mindful of possible CSS leakage, and then when developing new features, that would help. So that's why I also include this container style queries, which is pretty new and is still developing. So if somebody can catch it while it's still not fully yet up, that would be nice. But for mitigations, which is basically blocking certain browser feature, as I said, it needs to be more granular than just blocking the full feature. Like lazy loading, you cannot just block it. You have to see whether, it's repeating, it's in a row of different elements, because what I described is a naive approach. The full attack is more described in the paper, where you have a very big construction of different elements in the same row. So you need to find these patterns, I think, that would help.
Yeah, very good. Thank you. The reason I ask is just because it's like the idea of adding these generic rules from other lists seems like a cool idea in practice, but I think that just makes the life of filter list maintainers way harder, because we have to deal with all of these realized variables.
Yeah, and then you have more people pinging you about issues with rules they will never have to like discover before. Yeah,
complicated problem. Thank you.
I'm a little bit familiar with the Fingerprint.js stuff, because they have a GitHub repo which actually outlines the specific element they're trying to target, like the specific bait rules. It's something similar to that, where you basically got various bait rules that have triggered. Because I think how Fingerprint.js does it, there's a section for easy lists, like 5 or 6 roles, and there's a section for easy privacy, 5 or 6 roles, and then pretty much every other supported subscription will have bait rules for each. And I only have control over obviously a small section of that. Is that similar to what this is? It's basically just some bait rules saying if triggered, we know what you're running basically.
Yeah, I mean, so Fingerprint.js uses a wide plethora of techniques. So it could do like canvas fingerprinting, it could do like viewport fingerprinting, font fingerprinting, right? So I would treat kind of Fingerprint.js as a lower bound of possible attacks, because it's publicly available. And to recall an example that I went through with my own normal like research, I found like scripts that translate their code into a bytecode that is runnable through like a obfuscated JavaScript VM, right, to like fingerprint the user. So not sure exactly how much we can extract by just triggering behavior using like or tracking behavior, because it could be very wide possible ways to fingerprint.
I think Fingerprint.js knew that we were watching, and they started using base 64.
Yeah.
They started encoding their baits to avoid detection. It wasn't too hard to get around.
But encoding the source code is not the biggest issue. They're starting to encode the behavior. So usually you used to look at, am I seeing a lot of APIs being fired that will be fingerprintable? And am I seeing a lot of network requests that is carrying this payload, right? So that's a way to detect. Now they're like putting a lot of different ways to fake network requests so that they can go around like state-of-the-art detection.
Hey there. Fascinating talk. Thank you so much. You mentioned that element zapping can amplify the problem, which sounds shocking. Sounded shocking to me. But on second thought, I was wondering, how much does it actually amplify the problem? Wouldn't it also be very expensive to detect that? What are your thoughts around that?
Yeah. So, I mean, my idea behind this is not coming from like advertisers trying to fingerprint. It's mostly coming from the anti-adblock community, right? Because if the anti-adblock community tries to embed purposefully an element that you would be most likely to try to zap, right? Then they basically have an identifier on you for a long while, because they can randomize this element, right, to just appear for you, or in some sense, right? So yeah, as an anti-adblock, that's a very advanced technique that I could use to like just try to detect specific people using specific lists, right? So I cannot quantify exactly the increase in the risk, because it's also element zapping is an emerging kind of pattern. So we have to see where that goes as well.
Thank you.
I'm on. Okay, well, thank you, Said. This was a very engaging presentation with lots of questions.